Good morning. We will continue on our discussion on bipolar junction transistor. So, in last class we have seen that what should be the complete biasing circuit for a common emitter amplifier, right. So, this is a common emitter amplifier, right. So, what we have discussed so far that in previous cases we have seen that to DC bias this we need a bias potential VBB, right. Now, our objective is to minimize the number of DC sources if possible to a single supply source only. So, from this VCC supply source we will generate this VBB. Okay. How we are generating this? Using the potential divider network. So, this is known as the potential divider bias. Okay. The biasing voltage of the base emitter junction is generated by utilizing a potential divider network. So, this is known as the potential divider bias. Okay. There are other biasing technique that I will discuss in later classes. So, now we have discussed the role of these coupling capacitors, right. So, what is the role of these C1 and C3? To couple the AC source at the input and to couple to the next stage load. Okay. And the purpose of this coupling capacitor is to block the DC component and to pass the signal frequency, and its value is chosen such a way, so that the frequency at that frequency this should behave like a short circuit. And what is the role of this? This is known as the bypass capacitor. What it is bypassing? It is bypassing this emitter potential to the ground. Okay. So, what we will do? We will first find the DC analysis, we will find the DC equivalent circuit. While finding the DC equivalent circuit, what we will do? We will consider this capacitor as open circuit. So, all the AC sources we will not consider. So, we will redraw this circuit excluding this cap and the associated circuit. We will find the DC Q point from the input side as well as from the output graph. Then we will start to proceed to AC analysis. Now, you see we have figured out the Q point, right. Okay. Now, this Q point, this DC value is already known. So, do you need to again calculate the total value? You do not need, right. So, if you can get this AC value only, you do not need to calculate the DC value again, right, because that we have already calculated in DC analysis. So, rather than solving the complete expression, what is the complete current expression? Exponential, right. IC is equal to IS exponential VB by VT. We should not follow that nonlinear equation. Rather than what we will try to follow? The approximated linear equation. Okay. For example, IC is equal to beta IB, okay. V0 is equal to minus GMRC. So, those only the AC component we will try to figure out. So, that if we add or subtract from the DC value, we will get them total value. Okay. So, in AC analysis now you see, so in AC analysis we do not need to consider the DC portion. So, what we will do? All the DC sources should be grounded. If it is a voltage source, so this DC voltage in that case we will consider as if ground. Okay. Why? Because we have already reached the Q point. Now, we only want to see the effect of this AC sources. Okay. So, what are the steps? Find the AC equivalent circuit, then what we will do? We will sort this, right. While finding the AC equivalent circuit, this cap should be behave like a short circuit, and if there is any DC voltage source, make them equal to 0 or sort them to the ground connections. And if there is any current source, DC current source, what we will do? open them. We will replace the transistor by its small signal AC model, the small signal model, that 2 port network, we will draw that small signal model. Okay. So, let us see, and finally, if we use the superposition, we can get the total AC plus DC current. So, let us see the steps. So, this is the complete circuit and this is our DC equivalent circuit. What we have done? We have considered that cap is open and we have separated these two portions are disconnected. We will only consider this circuit. Okay. So, now what is our objective? To find out if VCC is given and suppose few parameters are given, then our objective is to figure out what is the value of R2, what is the value of R1 and so on. Now, this is the AC equivalent circuit. What we told, that we will consider that this cap is shorted. Okay. Now, if this source, if it is having any internal resistance, that we will plot. Suppose it is given that Vi is having internal resistance of 1 kilo ohm. So, it is drawn, the capacitor is replaced by a short circuit. Okay. Similarly, at the output it is given that there is a output load resistance, and you see this emitter junction now is there is a shorted, right. So, this resistance actually it will be not there, as if it is not there, is not it. So, this is my AC equivalent circuit. So, now what we will do? We will all the DC sources we will make it equal to 0, right. So, VCC, that is you see it is, this is a signal of ground. So, this is 0. So, if it is 0, now this RC comes in parallel to this R out, right. This is also grounded, this is also grounded. So, they are parallel connections, right. This node is common node. So, it is something like this. Right, and if we redraw this, it will be looking like, suppose this is my X node. So, this will be my X node, this will be RC and this will be RL, and these are sorted to ground. So, that is redrawn here as a parallel circuit. So, at first glance, if you see the complete circuit, you will be astonished how this RC is coming in parallel to RL, because in complete circuit or the DC circuit it is not, but in equivalent AC circuit what we are considering, this is our total current na. I have a DC component, I have a AC component. So, if we consider the total circuit, then this is not true, but for the only AC component this DC part is equivalent to 0. So, now the circuit is redrawn, and in that case RC and R0 coming in parallel. Okay. So, what is the equivalent output load now? What is the, if I see this is output, what is the equivalent load? Previously it was only RL, right. Now it is RC parallel RL. So, suppose if you find out the current IC, what is the drop here? And this drop is minus sign, right. This is not sourcing, this is sinking actually. So, this is minus. So, this should be your V0, right. If I multiplied Vi and if I divide this with Vi, then this will be my small signal gain. Understood? What is the output? I0 into V0. Now, for this AC equivalent circuit, my equivalent output resistance is RC parallel RL. Okay. So, through this equivalent circuit, how much current is flowing? That is minus IC. So, the voltage gain is minus IC into RC parallel RL. Okay. I will discuss this once again later. So, let us see that what is the structure, what is the AC equivalent circuit. Okay. So, at the input side what is happening, you see now R1 and R2 coming in parallel, but in complete DC circuit it is not, right, because now it is redrawn that this node is grounded. So, this node and this node they are coming in parallel, both are grounded. So, I have to just redraw the circuit, that is it. Okay. So, it is also redrawn. So, what is the equivalent resistance at the input side? Similarly, R1 parallel R2, that way we will simplify the circuit. Okay. So, this is not the, if I ask you to draw a AC equivalent circuit and if you draw this circuit, suppose this circuit, then it is actually not true, right, because there is no biasing, who will take care that it is in active mode, right. So, this is not the this is a AC equivalent circuit, this is a second step, not the, if I ask you to draw a AC amplifier, a small signal CE amplifier, then this is the circuit. Okay. Sometimes the student just draw this kind of circuit, but this is not true, this is a approximate AC equivalent circuit. Now, this is our hybrid pi model. So, this kind of structure we have already seen in the first chapter, and some of you were wondering that what is this circuit. So, let us tell you that this is a model for the BJT, for which case AC signal. Okay. This is not a large signal means DC plus AC. Okay. So, in large signal model your current expression is exponential. Okay. So, in large signal model there has to be a diode, right, at the input side. If you remember, in large signal model there was a diode at the base emitter junction, right, rest of the stuffs were almost similar, but this is a small signal model and there are several model. So, this is one of the favorite model, that is hybrid pi model. So, what we consider that between base and emitter a small resistance is there. Okay. Base emitter junction a equivalent small resistance is there. So, that is modeled by R pi. Okay. We are terming this as R pi. Say for this moment we do not know what is the value. Let us assume that there is a input at the input side there has to be a resistance, right, as the base emitter junction, base junction is base is very thin. So, it will offer some resistance. So, that is that resistance. Okay. So, R pi. What is the value of base current? Very small, right, compared to IC current and IE current, base current is very small. So, what you can assume this resistance value should be high or low? It should be high. Okay. So, R pi generally we will see that what are the values, those things we will check. What is this current source? GMVB. This is a dependent current source which depends on which voltage? Base emitter. This base and emitter, this potential will actually define this current, that is the meaning. Okay. So, we know if we multiply VB with transconductance we will get current. Transconductance means del IC by del V will cancel out. So, I will get only I, right. Del IC means small current, AC current, right. So, this is GM into VB. Okay. So, this is equivalent to your IC, right. So, this small signal is modeling what? This small voltage source dependent source is modeling IC. This terminal is my base, this terminal is my collector. Emitter, generally emitter you have seen that it is generally grounded. In AC equivalent circuit we see that even if there is a resistance we considered it the emitter terminal. In AC circuit it is we consider as a grounded. So, we can redraw this small signal model as this node is a. So, these two input side node, one is BC, another terminal, one is B, another terminal is E or ground, right. E is sorted to ground. So, this is B, the input port is B and E, output port one is C, another is E or ground. Okay. So, this is my 2 port network. What is my input port? B and E, that is base emitter. What is my output port? C and E, that is my collector emitter junction, right. Now, between collector to what it is telling, if there is a current source, this IC, this is behaving like a current source na. So, what you know, if there is an ideal current source, its equivalent resistance should come in series or parallel? Parallel. Its value should be high, right. So, there should be an high value flowing through high value resistance from collector to emitter. You see, these resistance are not there, right, we are modeling them, right. So, physically are there any resistance? Physically there is no resistance, but what we have seen, the current expression is like this. So, this zone, if it is flat, this R naught, there has to be a high resistance, right. What is this R naught? Suppose this is Vc. So, del Vc, this is Ic. So, what is the value of del Ic? Almost 0, right. So, this R naught will be ideally very large, agree. So, this is nothing but, so do not get confused that there is a resistor or something like, this is a model. We are modeling the behavior of the BJT characteristics, okay, because the current is flat in the which region? Active region, right. So, this flat current, this is you see like a, if I have a constant current source, irrespective of my voltage, this should provide me a constant current, right, is not it? If I have a constant current source, my load voltage may vary, but the current should not vary. So, you see this is the same nature, in this region this is the same nature. So, this I can model with a current source. What is the model of a current source? RS in parallel. What is the value of RS? In first class I told you, if there is a voltage source, series resistance is 0, if there is a current source, parallel resistance is very high or infinity, ideally infinity, right. So, that we have just replaced, that is it, nothing else, okay. So, if you are afraid that what is this, do not get afraid, this is just we are modeling the characteristics of this BJT. What is the input characteristics? A small current IB is flowing. So, we model a internal resistance R pi. Between IC, between C and E, a dependent current source IC is flowing, that we model through a GM into VB. And as this is an ideal current source and in the active mode it is almost flat, so we have put another R naught resistance, okay. If it is ideally flat, this R naught should be there or not there? It should be not there, it is a infinite resistance, means it should be as a open circuit. But if we consider the early effect, then we will be having a R naught resistance, right, this slope will be providing us the R naught, clear. So, let us see what are the values GM. GM is equal to del I by del V, and at the Q point, so this is, you remember always, this is we are doing not at ground, the AC circuit is equivalent to ground, but that we have to add with Q value. In AC model, we are only calculating the small signal, because DC is already calculated. What is that DC value? At the Q point, right. So, at this Q point what is my GM? Okay. At this Q point what is the collector current flowing? DC current, collector current IC. So, we will put that IC. What is the thermal voltage? Vt. So, GM is equal to IC by Vt. So, what we have just discussed, that R naught is equal to approximated as Va by IC, and these values of IC is at Q point. Now, there is a relationship between, I told you that R pi. So, this relationship how they are derived, that we will discuss later. So, now just note down these values, and we will, I told you repeatedly that I will be most of the things I will repeat again and again, so that you get acquainted with this. Okay. So, few terms we will again cover later. So, for this moment you just remember that R pi is equal to beta by GM, or beta is equal to GM R pi. Okay. So, let us see what it is trying to say. What is the R pi? Input resistance. What is the resistance? R is equal to Ohm's law, R is equal to V by I. So, this is my first hint. So, what is my, at the Q point what we equivalent voltage we are considering? Vt. And what is my input current? IB. So, this should give my R pi. Okay. So, you see this IB is replaced by IC by beta. Okay. And we already have calculated that IC by beta is GM, right. We already have considered that the GM, that is del IC by del V, that we have at the Q point we have approximated as IC by Vt. Okay. So, this IC by Vt we will replace by GM term. So, this is coming equal to beta by GM. Okay. So, this Vt terms is coming because the we have done the calculation, the scientists have done the calculation, and at the Q point it is shown that this Vt value is approximated. This at the Q point or the DC quiescent point, this is, if we calculate the GM expression, effective transconductance expression, then this Vt is coming, okay, 25 millivolt roughly is coming. So, at the input side also, input resistance also Vt by Ib, that is coming equal to beta by Gm. Why? Because Ic by Vt is Gm. Okay. Ic by Vt, always remember del I by del V is transconductance, del V by del I is resistance. So, this is transconductance. So, these two term you have to remember, and rest of the relationship will come automatically. Okay. So, this is our hybrid pi model. So, we can have two model, one is the dependent source is depending on the input voltage, then you have to draw a Gm into Vb, or you can draw a dependent current source, then Ic is equal to beta Ib. This is a dependent voltage source, this is a dependent current source. Okay. So, this current source is depending on the input voltage, this current source is depending on the input current, that is the difference. Both model are equivalent, both are telling about the small signal model of which one? NPN transistor. So far we are discussing NPN, na? We are discussing NPN bipolar junction transistor. So, this is a model, this is not the, I am again telling you, this is not the real circuit, this is a model of the behavior at which signal? AC signal. This amplitude of this AC signal should be large or small? Small. Why small? So that it remain in the active region, the linear amplification range that is satisfied. You will be always seeing this term small signal, two terms are, this means two terms. One is the signal is AC and next is the amplitude of the AC signal is small. Why small? Because we have seen that if it is big, then it may, the equivalent circuit may get clipped, it get into this saturated region. Okay. So, that is why we are always telling that this is a equivalent small signal model. Why? Because I told you the overall response may not look like a linear response, but if we break it into smaller chunk, it can be always approximated as a linear expression. So, what we are actually doing? On top of the Q, we are breaking in a small chunk. So, if I am considering this, here has to be a my Q and then the AC, clear, DC plus AC. So, on the DC point, what is that DC point? That is my Q point. Then we are considering a small signal and approximately use this model. So, that my, now this expression you see, there is no exponential expression, all expression are simple, right, like a ohmic expression, V is equal to IR, right, that is only you do KVL and figure out the current, and then what you have to do final to get the total current. Suppose you have figured out this, then you have to find out the DC value, add it to that is it. So, this step generally is we do not say, but to find out the total current, this is your, we are doing this small signal analysis, we are figuring out this, and doing the DC bias and DC biasing, DC analysis, we have already calculated this. So, there is no point to recalculate that once again. Okay. The simulator, it will take more time, the equation is complex, or the human person, he has taken pain to calculate the DC biasing, calculate the DC value IC, VC. So, why should he do it again? So, rather than solving the complete nonlinear expression, what is better to do? Do the small signal analysis, find the delta term, add it. Okay, this is the main objective. So, you see this is the complete expression. VB is equal to, now this VB, if IB current is flowing through R pi, this VB can be replaced by R pi, IB into R pi. Okay. Now, in previous case we have just figured out that R pi is equal to beta by GM. So, complete VB we can write down, VB is equal to IB beta by GM. Okay. Now, this GM VB, this is this VB replaced by IB R pi, or this is equivalent to beta IB. So, same thing is written in different form. Why? Because in some problem maybe this form is suitable, suppose this variables is given, in some other problem maybe. So, all the expressions are written, but you do not know remember all the things. If you remember one equation, other equations is always you can derive. Now, what is IC? Is approximately this GMVB is your current, because why? This other branch current, this thus unknown ideally is infinite, right. So, this is goes to 0. If we do the KCL here, so this branch current plus this current, this is my IC, right, but we can approximate it as if beta IB, easier way, right. So, this table summarizes all the expressions, and we have seen that. So, you see this is our ideal model. Why ideal? We are considering R out is equal to infinity, the current is flat, or you can say this is without considering the early effect, and this you can consider the considering the early effect. Okay. What is the difference? Here we are considering that there is the C and E, between C and E the resistance is infinite. So, we are not drawing that simple model, only R pi is there and GMVB current source is there. This is transconductance model, this is current source model, IC is equal to beta IB. Same hybrid pi model, now we are adding on the second order effects or the more real life effects. So, this is like current is like this flat, but here we have seen that okay, current is not actually flat, it is little bit increasing. So, this increase of current or this slope is included by modeling a parallel resistance. What is the meaning? Some extra current is coming na, you see as Vc is increasing, current is also increasing. So, to model that, if this base emitter voltage VCE, if this is more, then what will happen? The current through the resistance will be also more, right. So, that will be added with this dependent current source and I will get this extra variable, that is it. Okay. So, this is a real life approximation or the considering the non ideal effects, this is a ideal, only ideal. Okay. So, same BJT, this is a ideal model, this is a non ideal model, clear, and these are the all the values that we just discussed, that R naught is equal to what we say early voltage by the collector current at which point? At Q point. R pi is equal to Vt by Ib. Okay. And what is Gm? Gm is equal to Ic by Vt. Okay. So, remember this beta is equal to Gm R pi, then you will be having relationship between R pi and beta. Okay. What is your Gm? Del Ic by okay. What is your R pi? Say del Vb by del Ib. Ib is equal to Ic by so, you see this beta is equal to Gm R pi, that you can calculate like that way. Okay. So, this is your Gm term, this is your R pi term, if you multiply them what remains? Beta. Clear? So, if you forget you can just recalculate them. Now, this already we have discussed, right. Alpha is equal to beta by beta plus 1 and beta is equal to alpha by 1 minus alpha. So, the other terms can be derived. So, if you remember one terms, the other terms can be derived. So, for this small signal model, if you follow these equations, one is GM equation, what is the value of GM? IC by Vt, what is the relationship between R pi and beta? Beta is equal to GM R pi, and relationship between alpha and beta. So, then you will be able to solve the problem of any electronics BJT circuit. So, this is one example. Okay. So, let us read out what the circuit is saying. This one circuit is given, you see what is the supply voltages? Plus minus 15. What is the base potential? 0. Will this circuit work? Base voltage is not there, 0. Will this circuit work? Yes, because emitter voltage is minus 15, base voltage is 0, the difference is 0 minus of minus 15 is equal to 15. So, effectively the base emitter potential is positive, but if this potential were at ground, then this circuit may not work. Okay. Because this is minus volt, this potential is positive, base is higher than the emitter voltage, base emitter junction is forward biased. Because this is a very high voltage, you are sure that okay, base emitter junction is forward biased, right. Collector potential is higher than the base potential, NPN, right, this is N potential is higher than P potential, collector base is reverse biased. So, this BJT is biased in which region? Active region. So, this is the first step you have to figure out, okay, in which mode. Okay. Base emitter forward bias, collector base reverse bias. So, this is in active mode. This is the first thing you will try to figure out. Rest of the thing is to find out the base current, collector current and so on. Okay. Now, what they are saying that beta for beta is equal to 100, Vb at 0.7. If beta is 100, Vb is 0.7 at IC is equal to 1 milliampere. So, it is given that if IC is equal to 1 milliampere, my Vb is 0.7. Why it is given? So that we can recalculate the value of Vb if IC is varying. IC voltage if it is varied, actually the what is the input? Input is Vb. If Vb is varying, IC will vary, right? And from that expression we can recalculate this, right? Your IC equation, IC is equal to Is exponential Vb by Vt. From that you can recalculate the value of Vb, right? Vb is equal to log of something, right? Some. So, that we should find out, that is why it is given, okay, because Vb is also varying, right? Na? Vb is also varying, this is my Vb, this is also varying. So, at 0.7 value is given, that at 0.7 the IC is 1 milliampere. Next, what is given? Design the circuit. Now, you may wonder that circuit is already drawn, then they are asking that design the circuit. What is the meaning? To meaning is find out the unknown values. Design the circuit means find out the circuit component that are not given. For example, RC and RE not given. This source voltage is given, this source voltage is given, this source voltage is given. What is not given? RC and RE. So, design the circuit means to find out the unknown values. Okay. If a current of 2 milliampere flows through the collector and a voltage of 5 volt appears at the collector. So, this voltage is given, this voltage is given 5 volt. So, if this is 15 volt, this is 5 volt, find out the current is 2 milliampere, what is you have to figure out? RC. Do it. RC is equal to, how to do it? 15 minus 5 by 2. So, we will just do that, 10 by 2 is equal to 5 kilo ohm. So, RC mil gaya. Okay. Now, what we will do? We will try to find out the for 2 milliampere current, what is my VBE. One hint is given that VB is equal to 0.7 plus some extra, right, current is now more, from IC it is higher. So, VB should also be higher. So, 0.7 plus VT ln IC2 by IC1. Okay. So, VB is equal to this expression, you can, if you forget, you do not need OD, just remember one expression, IC is equal to IS exponential VB by V2, VB by VT. This is, you termed it as IC2, you figure out another IC1, you just from there VB1 and VB2 you try to find out what is VB2, that is the objective. So, you will get this expression, VB2 is equal to VB1 plus VT ln 2 by IC2 by IC1, that is coming as 0.717. Because the current is exponential in nature, you see base voltage is varying by only 0.17 volt, but the current is almost double, right. Base emitter voltage you see varied by 0.017 volt or 17 millivolt, but the current is as if just 50%, 1 milliampere to 2 milliampere. Okay. So, this done. Now, what I will do? I will do the KVL at this loop. What is the KVL? 0 is equal to VBE plus this drop IERE. Okay. So, from this we will get the IE we can calculate. So, let us calculate IE. IE is equal to IC by alpha, from where alpha is you are getting, beta is given, na? Beta is given. So, alpha is equal to beta by beta plus 1 0.99. So, I is equal to IC by alpha 2.02 milliampere. So, RD is equal to this V potential is given, this is minus 15 volt. So, 0 is equal to VBE plus IERE plus or minus, I am writing it VEE, in place of VEE you put minus 15 volt, then your KVL is complete. Okay. So, most of the problem will be of KCL and KVL. So, we arrive the unknown potential RC, unknown resistance RC and unknown resistance RE. So, that completes the design, and you can cross check that okay, the assumption, initial assumption that base emitter junction is forward bias, collector base junction is reverse bias, this is in active mode, that is satisfied. So, these are the steps, and most of the time you will be find out that the steps are, if you follow the rules, then most of the steps are very easy. Okay. So, let us close it today here, and we will continue from this onwards.